Hello students, this is Professor Espinosa for ITEC621. I'm recording this lecture for lecture 3.3 OLS Assumptions. Let me go back into the slides here. So in this particular slide, we're going to be talking about the necessary assumptions that need to be tested or need to be in place before we can use the OLS assumption. Before we start with this, I wanted to bring to your attention this predictive modeling summary here. The predictive modeling summary, if you have this PDF in the same directory where you have your slides, you can click on this and it'll open. If not, just go to Blackboard and you'll find the predictive modeling summary in the lecture section for this class. Let me put the predictive modeling summary on the screen just to explain what it is. The first page looks like this, and it gives you a little bit of the process for model selection. It's supposed to be a good guide for you. Please note that when you take the exam for this class, you will be allowed to have this document with you. So if you have, I encourage you to take a look at this model and method summary. It's supposed to be a guide to help you select the right model. And you can make any margin notes on the sides and bring that to the exam, and that will be perfectly fine. So in this first page, we have the process to build a model, and I will discuss this a little later on once we cover cross-validation testing and machine learning. Here's the analytics life cycle, which I already discussed in one of the introductory slides, so I'm going to pass that. And here is the process to select a model by a graphical process model. And as you can see, we end up with a cross-validation testing. And then this is what the cross-validation testing is all about. I'm just going quickly through this because we will be covering this in more detail later in the class. I wanted to show you this part of the model selection document. It's a template. We're going to be talking about OLS assumptions today. And I put together this table. If you look at the yellow square up at the top, you can only use ordinary least squares if those assumptions listed in that yellow square are met. We don't have to be too strict about it. If you have a model that kind of complies with these assumptions, but to some extent, not purely, I think it's okay to use the OLS. And we're going to be discussing that as we cover different methods in the class. But if those assumptions don't hold, I have a whole bunch of transformations that you can do here. You can do a weighted least squares. We're going to talk about this later today. We can use standardized OLS. We can do log transformations. This is supposed to be a summary. Don't try to understand this now. Wait until we cover the particular topic and then use this as a summary guideline to help you select the right model or the right transformation. This is the next page. When to use generalized linear models, when to use rich regression, when to use lasso, principal components, and so on. Okay, so I want to go back to the slides. That's all I'm going to say about the predictive modeling summary now. But I want you to download that PDF and have it with you as we go through the different modeling options in the course. So let's talk about the OLS assumptions. We start by looking at what is OLS. OLS is a method that helps us fit a regression line, and it uses that formula that you see on the screen. That formula is a matrix formula, so the coefficient vector is computed as the matrix of predictors transposed, multiplied by the matrix of predictors, and then inversed, multiplied by the predictors transposed, multiplied by the response vector y. And if you apply this formula, boom, you get the OLS coefficients just like magic. And you know, software like R can do this very quickly because R and Python, they're very good about multiplying matrices and stuff like that, so we don't have to worry about all that. But the thing is that All of this is based on simplifying assumptions. The people who developed this formula, as I explained in class, had to make a lot of simplifying assumptions because the solution for ordinary least squares is very complex. It's very, very complex. So you need to simplify the model in order for the formula to work. For example, if the average errors is 0, there's a lot of terms in the proof that will cancel out. If the variance in the model of the error terms is constant, a lot of terms will cancel out. So, but if those assumptions don't hold, then the formula is not correct really. You can't really use it. Okay, so let's go through this in more detail. So what is blue? What does it mean to be blue? Blue stands for best unlinear unbiased estimators. Okay, so if all the OLS assumptions hold, mathematically it can be proven that the OLS line is blue. It's the best linear unbiased estimation. In other words, it's the best model you can have for your predictive model. So that's, so you always start with OLS and try to, fit a model that gives you, has good predictors, and you test the OLS assumptions, and if everything works out, that's the best model. You're done. But many times the assumptions don't hold. So we're going to talk about that today. So best means that the estimators have the lowest variance. As I explained before, if I take a random sample of the data and I estimate a model and I get beta coefficients, and then I take another subsample and run another OLS model and I compute the beta coefficients again, if I do this many times and the coefficients have a lot of variance, I get different results with different subsamples. We say that the model has a lot of variance. If the coefficients are pretty much similar, pretty close to each other for each random subsampling, then we say that the model has low variance and it's a more stable model. Linear means that the y or the response variable or the dependent variable is linearly related to the x's. So if you were to look at a scatter plot, you would see the dots in the scatter plot aligning sort of like in a straight line fashion. You don't see a curve or some cyclical pattern to the data points. And unbiased means that the beta coefficients represent the true effect. We never know the true effect, but we may have an idea what the true effects are, and if the beta coefficients are not representative of a true effect, we say that those coefficients are biased. And again, if the OLS assumptions hold, the OLS is unbiased. Okay, then if that happens, then we use OLS and we're done. We have parametric versus non-parametric methods. As I explained before in class, parametric methods are methods that rely on assumptions. We have these complicated models, and we simplify the models by using assumptions which constrain the model. It limits the model, what the model can do, and the cases in which we can use the model. But the good news is that when we have those parameters, the model gets simplified and it's a lot easier to estimate it. Examples of parametric models are OLS, logistic, linear discriminant analysis, and so on. Non-parametric methods, on the other hand, they don't rely on assumptions. You can use them many times. You don't need to test anything. K nearest neighbors, you just find, let's say, 3 nearest neighbors, and you take averages for those 3 nearest neighbors, and you're done. You have your prediction right there. Your prediction is going to be an average of the response value for the 3 nearest neighbors in the data sample. Same is true for decision classification trees, support vector machines. We don't need to test any assumptions. OLS is parametric. That means we need to worry about assumptions. So let's go through the assumptions one by one. And I want you to think of this conceptually. Conceptually, what does it mean for I to be continuous? It means that our dependent variable or our response variable is a continuous a continuous value, which means it has decimals. It can be any value in a continuous range. So it can be 2.5, 2.33, 5.444. That means that that the response variable is continuous. So how do we test for this assumption? Well, we can look at the data. Sometimes we look at the data and we see that the dependent variable is binary, 0, 1, or we see that it counts from 1 to 5 or 1 to 10. Then those are not continuous. We don't even need to do any testing with it. Okay. So basically we observe for those values, and if they're continuous, then we're okay with this assumption. If the values are not continuous, then we need to use a different method. So we use methods like the generalized linear model, GLM. We're going to talk about this a little later today. And we try to find the appropriate data distribution for that model, which will fit the data better. Okay, we're going to talk about that later. We can use classification methods if the data is binary, or if the data is multinomial classification. Binary would be 0, 1, yes or no, true, false, success, failure, or it could be a classification like, rural, urban, and suburban categories, or undergraduate, freshman, sophomore, junior, and senior classifications. If our data tries to predict those values, we call that a multinomial classification. If it's just a 0, 1, we call it a binary classification. So if y is not continuous, we need to find the appropriate method to work with binary or multinomial classification data. Assumption 2, the errors have to be normally distributed. Many times we look at the response variable y, and if y is not normally distributed, chances are that the errors are also not normally distributed. So a quick test to see if the errors are normally distributed is just to look at the dependent variable y and do a QQ plot or a normal distribution graph and see if y is not normally distributed. If it's not normally distributed, we can still run the regression, but we need to inspect the residuals carefully. And chances are that if y is not normally distributed, the error will not be normally distributed. So it will be important to test that the errors are normally distributed. We can use residual plots, QQ plots. We can do some normality test. If the errors are not normal, then we need to do some transformations depending on the type of situation we have with the errors. We might need to log the y's. We might need to do a box-Cox transformation. We're going to spend 2 weeks talking about transformations in this course, starting next week. So here's an example. When you do regressions and you do the regression plots, as you probably remember, you get 4 plots when you run a regression. If you do a plot of the regression model that you run. The plot to look at is the upper right quadrant. That's the QQ plot for the residuals. So it's very easy to check. So you run your regression model, you look at, the first thing you want to do is look at your residual plots. And if the dots don't align along that straight line, then the residuals are not normal and we need to do some transformations. Okay? Assumption 3. For assumption 3, we're saying that the predictors are independent or they're uncorrelated. We've talked about this when we were looking at correlation. We always said that a good model is one in which the predictors are highly correlated with the outcome variable, but the predictors are not correlated with themselves. In fact, if the predictors are correlated with themselves, we're violating this particular OLS assumption. Now, we can have some correlation, and that's tolerable. But if the collinearity and the overall correlation among predictors is very, very high, we say that multicollinearity is severe. And then it's not appropriate to use OLS. In this case, if we suspect that there is multicollinearity, we can eyeball this by looking at the at the correlation matrix, and if we see a lot of correlation among the predictors, we can begin to suspect that we may have a situation with multicollinearity. We're going to deal with multicollinearity later on when we discuss dimensionality, so we're going to look at this very carefully later. But just to let you know, there's two tests that we were going to do. One is called the condition index. The condition index looks at the overall multicollinearity of the entire model. It looks at all the predictors together. And then the various inflation factors is what we use once we've determined that there is collinearity in the data. We can use the various inflation factor to evaluate which variables are the ones that are contributing the most towards multicollinearity. If there is multicollinearity, we can try to select variables to reduce multicollinearity. Many times that's not very, doesn't help too much. In those cases, there are particular methods that take advantage of the collinearity in the predictors to build more robust models like rich, lasso, principal components, partially squares. So if you have high multicollinearity and subtracting variables from the model doesn't help, this is the way to go. Assumption 4. Assumption 4 means that the x's and the y, that means the predictors and the response variable are linearly related. So we can, if you do scatter plots of the response variable with each of the predictors in your model, you should see a scatter plot that looks roughly linearly aligned. You don't see a curvilinear pattern or anything like that. We can just do scatter plots for all the predictors against the y and see visually if there is some linearity or nonlinearity. If we suspect that there's no linearity, what we can do is introduce polynomials. And this is actually easy to test. So if you have a model with an x predictor and you suspect that it's not linear, you can take x squared, you can add x squared to the model with x and do an ANOVA. And if the x squared adds significant predictive power to the model, then you know that the model of the assumption of linearity is not holding well. The good news is that you can correct with nonlinear models very easily, and we're going to spend a whole week talking about this, maybe even more. Assumptions 5 and 6, observations have to be independent. What that means is that one data point should not influence the other data point. For example, it is snowing right now. If I take hourly data on the weather, chances are that it will be snowing an hour from now. And if I take data an hour later, it will be still snowing. If it's not snowing, chances are it will not be snowing in an hour. Or if I take the temperature in a room, I'm trying to predict how a thermostat reacts to different temperatures. Same thing. You know, the temperature today, right now, will be roughly the same as the temperature in half an hour. If I have a group of close friends and I'm giving them a survey to complete, chances are they know each other, they have similar preferences, and they're likely to respond similar. So they're influencing each other. So we say that these observations are dependent. And one of the OLS assumptions is that the observations should not influence each other. Okay. The model that we're going to look more carefully about independent errors are when the errors are not independent, when the errors are dependent. That means that the error for one data point is closely correlated to the error for the next data point, either positively or negatively. We see that, for example, in economic data that is seasonal. When we're in an economic boom, there's growth. We'll see good economic indicators for a while. And then if we go through the business cycle and we see a downturn, then we'll start to see some negatives. But the errors will be highly correlated. We call this situation serial correlation or autocorrelation. And it's very easy to test with a test called Durbin-Watson. And there's other tests that we're going to talk about a little later. Okay, and we're going to discuss a little bit of causal models, time series, and how to correct for serial correlation. We usually resort to lagging variables. However, if you have a lot of economic data and you want to do some serious forecasting, I recommend that you take a forecasting course because their forecasting models are quite sophisticated, and we can cover those in this class. All right, assumption 7 and 8, we have that the error, the average of the errors is 0. Now, you don't need to test it because the OLS formula already takes care of this. So it makes all the errors average out to 0. All right, so the solution will ensure that the average of the errors is 0. But it's an important OLS assumption. This other one is we had to test many times. And this assumption is that the error variance has to be constant. Another word for this is homoscedasticity. That means that if the errors are homoscedastic, I know it's a difficult word to pronounce, but you will learn it this semester. You'll be pronouncing it right by the end of the semester. If the error variance is constant, that means if we plot the error points along the predicted line, the error should look up like a even cloud of data. Okay, if they don't, if you see a pattern in the data, we say that the residuals are heteroscedastic, and that's the situation we need to correct. It's very easy to test. There are tests like a Bruch-Pagan test, and there are other tests that you can use, but we're going to use the Bruch-Pagan test. Very, very easy test to run. And then if we find that heteroscedasticity is a concern, then we can run a weighted least squares or WLS method, which we're going to be covering in the next lecture. Okay, so this is, if we want to look for heteroscedasticity, we look at the first plot of the residual plots in a regression. So we run a regression, we plot the residuals, and we look at the very first graph. And the very first graph gives us a convenient red line that shows us if there's a pattern in the residuals. Now you can see that the data points in this graph are fanning out. They're not constant. They're not a constant cloud of data points, but they're actually fanning out. So I would suspect that there is some heteroscedasticity in this residual. So we're going to have to test it, and we're going to talk about this in the next lecture. Now, predictive model selection. So those are all the OLS assumptions. So how do we select the right model? Remember, we have to select the right modeling method, and we have to select the right model specification. At this time, we're talking about the right model selection only. So first we try OLS, and if our outcome variable is quantitative, then we try OLS, we test the assumptions, and if the assumptions hold, OLS is blue. That's the model to select. If the response variable is binary or a classification data, we can run a binary logistic model or a multinomial logistic model and test the assumptions, and if they hold, then logistic is the way to go. If the OLS or logistic assumptions don't hold, then we have a whole bunch of things we can do, okay? We can try to find a model that addresses those particular violations of the OLS assumptions, or we can make the necessary corrections. We're going to talk about transformations in the next 2 weeks. Then another thing we can do is, depending on our analytic modeling goals, we can, if for example we're interested in just predictive accuracy, we're not too interested in interpretation, then we can do some cross-validation testing. And if the OLS model gives the best cross-validation testing results, even if some OLS assumptions don't hold, it may still be the most accurate model. So in the absence of better models, sometimes we go with OLS. So we're going to talk about cross-validation at length later on in the semester. If you do cross-validation testing and you find several candidate models that have good cross-validation testing results, and they're very similar results, I would select the most interpretable model. It's going to be one that's going to serve your needs better. Okay, So this is the model selection process, but in a graphical presentation here. So again, we decide whether it's a quantitative or a classification method. If it's quantitative, we go the OLS route. If it's classification, we go logistic route. Then we test the OLS or the logistic assumptions, and if they hold, we use OLS or logistic, depending on our outcome variable. And if the assumptions don't hold, then we need to evaluate the particular assumptions and select the right transformation or the right model, do some cross-validation testing, and then select the right model. Okay, so I'm done with this lecture. So it went, the time was exactly as I planned it, so this is nice. I want to then sign off and move on to the next lecture. Thank you very much.